Hi everyone, this lab tutorial video goes along with Chapter 9. We will essentially be combining all of the information from 9.1, 9.2, and 9.3 and putting it all together in one problem. Each one of those sections kind of breaks down the linear regression process into these little micro lessons, but it's kind of hard to see the forest for the trees. So we're trying to put all this information together in one activity for this lab. It's a lot of really heavy calculator work, so I really suggest taking notes on the different buttons that we use and the different stat functions that we go through as we complete this activity. So the situation is that a researcher wishes to determine if there exists a significant linear relationship between the height and the diameter for a particular species of tree. The table records the heights in feet and the trunk diameters in inches of 8 trees. So our sample size here is 8. Part A is, what would the scatter plot look like for this data set? You can do this in Excel, copy and paste the scatter plot from a graph that's automatically generated from that program. You could print this out and sketch it out by hand using the ordered pairs 70, 8.3, 72, 10.5, 75, 11, so on and so forth. Or you could snip a picture right from your calculator. So I want to show you how to do this on the TI-84. Your first step is to obviously put those two X and Y coordinate pairs in a list. So under the stat button, you would hit edit. And then in list 1, you would put your X values, and in list 2, you would put your Y values. So I went ahead and did that already. I'm just going to make a note here of what I'm putting where. So list 1 is X values, list 2 is the Y values, and these are the raw data points that I've collected from the field. So what we want to do now is turn on a scatterplot graph. So we're going to hit the second button, and then we're going to hit the Y equals button. And you'll notice right above it, it says stat plot. So I want to turn a plot on with 1 highlighted here. I'm going to hit enter, and then I'm just going to simply turn it on. It gives you little pictures for the type of graph you want to create. The very first one there is the scatterplot graph, so make sure that's selected. And then make sure that these two things are the correct list. So my X values came from list 1, my Y values came from list 2. So just make sure those are displayed properly and then hit enter. And I want to kind of zoom in on these points. That's really the only thing I want to see in the graph. It's not really important that I see the X and the Y axis. So to zoom in on these data points, we're going to hit the zoom button here at the top, right in the middle of the screen. And if you scroll down to option 9, I believe it is. Yeah, Zoomstat. If we hit Zoomstat, it goes right to these data points. I don't have to mess with the y-axis or the x-axis and create mins and maxes. It goes right to these data points, and I can see that scatter plot very clearly. If you want to look at these individual points, you can hit the trace button, and your arrow keys will just toggle through all those different coordinate pairs that we put into list 1 and list 2. So again, you could take a snip of that screen. I'll go back and do that real quick. Snip. And that's a quick little scatter plot of what my raw data points look like. Okay. Now in part B, we want to find the sample correlation coefficient and use it at the 0.05 level of significance to test it. So what does that mean? That means that I want to come up with a numerical value that registers the linear relationship amongst all these points. You can kind of tell that it looks like it's following some kind of upward trend, that there's some kind of linear relationship here. As X increases, so does Y. So I want to quantify that, and we do that with the correlation coefficient. The closer that value, and by the way, we call that value R, the closer that R value is to either 1 or -1, the stronger the linear relationship is. And we can test that with the Pearson correlation coefficient chart. And if you would like to print that out, it is in your textbook. So go to chapter contents, go to the appendices again, and it is table 11, critical values for the Pearson correlation coefficient. So I already have that downloaded. So we would test it at the appropriate level of significance, which I've already picked for you at 0.05. So let's find this on the calculator. It will do it for us. We don't have to do this by hand. To find it, we actually have to turn on a function from the catalog. So what you want to do is you want to hit the second button and then come down here to the 0 button. See where it says catalog? We want to hit 0 and scroll down. So you're going to want to hold down that arrow key. Scroll down until you see diagnostic. Whoa, I'm way past. Until you see diagnostic on. Diagnostic on. And once the arrow is next to it, hit enter. And then you have to hit enter again until it says done. So this turns on regression diagnostics. It will always be running in the background of your calculator unless you do diagnostic off, but it's not like it really takes up a lot of like space or memory or whatever. So it's okay if it's constantly running. Once you turn it on, it's going to stay on even when you turn your calculator off. So you really only need to do that once. Just make sure that it says done. So to get our correlation coefficient, we're going to use the lin-reg menu. So after you do your diagnostic on, from the catalog, you're going to hit Stat, scroll over to the calculation menu, so Stat, Calc, and then the fourth option down is lin-reg. We're going to hit Enter. And this is not only your regression equation, the map of this line that's going through the plot, but it also gives you your sample correlation coefficient. It's the last value here, R. So we've got R equals 0.8193565.045. That's our sample correlation coefficient, and we want to test the absolute value of R at the 0.05 level of significance. So how many points do we have again? We've got 8 data points. So at the 0.05 level of significance, we're going to test that at 0.707. 0.707. 0.8193 is definitely going to be greater than that value. So at the 5% level of significance, there is enough evidence to conclude that there is a significant positive linear correlation between the tree's height and its diameter for this particular species. So let's see here at the 5% level of significance, there is enough evidence to conclude positive linear correlation. Now, obviously, that's messy, and you should probably not write as messy as I do, but we're trying to go quickly here so I don't take up all of your time. Part C, find the coefficient of determination and interpret its value. Well, it is also an output of linear regression here. We can see it as the third line down here, R squared is called the coefficient of determination, and it is approximately 0.671. How we interpret this is as a percentage that can be explained by the relationship between these two variables. So we would say something to the effect of about 67.1% of the variation in the trunk diameter can be explained by the relationship between the height and the diameter. So that leaves about 33% of the variation that is unexplained by the relationship between these two variables. So it's just a proportion of the data that's explained versus unexplained. Part D, write the equation for the regression line that best fits this data set. Well, this is again an output of the lin-reg menu. It gives me the slope of the line, right, the coefficient in front of x, and it also gives me the y-intercept, which they call b here. So our regression equation, y hat, is equal to 0.47949666691 x, let's see, minus our intercept value, 24.086306644. At this point, we also want to save this regression equation in the y equals button. So with this in the command window, we want to immediately hit the y equals button. And while your cursor is kind of flashing here in this first equation, we're going to hit the variables button. And we want to scroll down to where it says statistics. And in the next menu, we want to scroll over to the equation commands. And I want to hit the very first one there that says REGEQ, regression equation. So really what that does is it just copies and pastes this equation from the lin-reg menu into the y equals button. Now, why do we want to do that? This is the line that best fits all of those scatter plot values. So like if I were to go back and do zoom 9, it would overlay those points with the line of best fit, the regression line. Kind of cool. Okay, so let's quit out of that. Part E says predict the trunk diameter in inches for a tree that is 74.3 feet tall, round to the nearest hundredth. So what this is asking is, okay, given this best fit line, can you come up with some kind of predicted value given some height? So really what we want to do is take this 74.3 and plug it into our equation. I'm going to let the calculator do that for me. If I set my table to ask, meaning I'm going to hit the second button and then the window button, see where it says table set here, second window, the independent variable, this is the independent variable here, x, I'm going to set that not to auto, but to ask for certain values. I want to ask specifically for the value 74.3. And again, once you do this table setup, you don't have to do this every single time, but you want to set that independent variable to ask. Then go to the table. Second graph gets you the table, and I want to ask that line specifically for the independent variable 74.3. And the output there is about 11.54. We're rounding to the nearest hundredth here. This is about 11.54 inches. So according to my regression equation, a tree that is about 74.3 feet tall is going to have a trunk diameter that's 11.54 inches. See how much heavy lifting the calculator is doing for us? All right, part F, calculate the standard error of estimate, round to 4 decimal places. Okay, well, the formula for the standard error of estimate, S sub E, is kind of ugly looking. It's the square root of the sum of the deviations between the observed y value, so the stuff that we put in L2, minus our y hat values, so values coming from the regression equation. Those differences are being squared and summed together, and we're dividing that by n minus 2. Okay, so this is again something that can be done by the calculator, little dicey in terms of the directions here, so I hope you can follow along with me. We're going to go back into our lists. So remember, I already have, I'll scroll back up here, I already have in L1 the x values and in L2 the y values. So in terms of my equation here, these are already in L2. I want to put the y hat values, so what I mean by that is taking all my x values that are in my raw data set already in L1, I want to take all those values and plug them into my regression equation. If I were to do that by hand, it would probably take me a little while to do that and then enter them all into a list in the calculator. The calculator will do this for us. So what I want to do is I want to put these predicted values in L3. Okay, so let me show you how to do that. Hit the stat button, enter on the edit, and scroll over to L3 and actually up into the title of the list, like have L3 highlighted. And what I want to do is in this list, I want to put the predicted values that are coming from the regression equation. The regression equation is in the y equals button. It's in y1. So with L3 highlighted like this, I'm going to hit the variables button and I'm going to scroll over to y variables. And I want to call the function, so hit enter again on function. I want to call the function that is in y1 right now. That's the regression equation. Now, what do I want to do with y1? I want to plug into y1 all the values that are in L1. So I'm going to open a set of parentheses and say y1 of second 1 L1. Okay. Now, if we hit enter, notice that the entire list 3 populates itself. So what the calculator is doing is it's taking 70 and it's plugging it into the y equals regression equation. The output there is then recorded in L3. Then it takes 72, plugs it into the regression equation in y1. The output is then recorded in L3, right? So it's doing this for every value in the list that we don't have to do it by hand. Isn't that great? So now what do I want to do? Okay, I want to take all the values in L2 and subtract L3, and then I want to square all those values and store that list. So from here, I'm going to do second mode, go back to my command window, and I want to put this together. So here's what I'm entering in my calculator in the command window. I'm doing L2 minus L3. I'm going to square that, and these values here, I want to store them in list 4, and then I'm going to do one variable stats on list 4, because everything that is in this list of squared deviations, I want to sum them all together, right? That's what this outside summation symbol means. So once I come up with all these squared differences, I want to sum them all up. So I'm going to do one variable stats on L4. I'm going to get that value and then divide it by 8 minus 2. I've got 8 data points. I subtract 2 degrees of freedom. Okay, so let's do that. Open set of parentheses. Second 2 grabs L2 minus second 3 grabs L3. Close parentheses. So those are the deviations. I'm going to square the deviations. And then I want to store that list in second 4. Okay, so it puts all those squared deviations in list 4. We could go and look at it by clicking stat and then edit, but I don't really need to. What I want to do now is do one variable stats on that list. So stat button, scroll over to calculate, one variable stats on second 4, L4. Okay, now we want to sum up all the stuff in that list. So this, the second option down where it says sum of x, that just means the sum of all of the entries that are in L4. So that's going to be 19, I don't know why that keeps coming up, 19.00775722. That's going to be in the numerator. That's the sum of the squared deviations, and I'm going to divide that by 6 and take the square root of that ratio. Okay, so let's do that. Second square root. Divided by 6. So that's going to be approximately 1.7799. 1.99. That is our standard error of the estimate. All right, last part, I'm going to put all of this stuff together using my regression equation, using my standard error of the estimate to create a prediction interval. This is like, the goal of this whole process at the end is, given some estimated tree height, can you give me a level of confidence to go with a lower and an upper bound that is going to give me an approximate trunk diameter, to a certain error value. So what we're really constructing here is the confidence interval y hat minus some error, trapping the true y value between it and y hat plus some error, where the error formula is really ugly looking. It's T sub c times our standard error of the estimate times the square root of something big and yucky looking, 1 plus 1 over n, plus the ratio n times our x naught value, which is the value that's given in the problem, like, what height in particular are we interested in, x naught minus x bar squared divided by n times the sum of the x squared values minus the sum of the x values quantity squared. I know, right? Isn't that ugly looking? Okay, let's go through and see if we can figure all this stuff out. First, let's figure out our T sub c value. This is assuming n minus 2 degrees of freedom, and we're looking at a 90% level of significant or confidence level. So let's pull up our T distribution, table 5. So I've got 8 data points, and we're subtracting 2 for the degrees of freedom. So I'm looking up at the line of 6 and scrolling over to the second column for 90% level of confidence. Looks like my T sub c value should be 1.943. 1.943. Okay, we're going to multiply this by the value that we came up with in part F, which is our standard error of the estimate, 1.7799. And I'm going to multiply this by the square root of 1 plus 1 over n, which is 1/8, plus 8 times the quantity x naught, which is 80, minus x bar. I gotta figure out what x bar is. Stat, calc, one variable stats on list 1, because that's where all my x's are. X bar there is 76.875. 76.875. I'm going to square that and divide it by 8 times, now the sum of the x values squared, that's the third option down here, sum of the squared x values, 47,447, minus the sum of the x's, which is 615 squared. Okay, when we plug this into our calculator, we are going to get something to the effect of 3.761. Now this is the error. This is the value that I'm going to add and subtract to my point estimate, which now I got to figure out what that is because it's coming from my regression equation. I'm going to plug in my x naught value into y equals and figure out what my estimated trunk diameter should be according to my prediction equation. So second graph gets me into the table again. I want to ask it this time for a height of 80 feet. And it looks like 14.273 is my y-hat value. So I'm going to add and subtract my error to my predicted value here. 14.273. Subtract the error of 3.761. And then I'm going to call that same thing back. And this time, instead of subtracting the error, I'm going to add the error. So my lower and upper bounds are 10.512 and 18.034. So we can be 90% confident that the tree trunk diameter will be between 10.512 inches and 18.034 inches when the height is 80 feet. Okay. And that's the last part for this particular lab. So it's taking you all the way from the raw data values, X and Y coordinate pairs, to creating confidence intervals for any one independent variable, right? So this could be any value somewhere in between those raw data points. You know, you pick something that was never measured per se, but you can still get a level of confidence and an approximate interval over which the true Y value could be obtained. So I hope this was enlightening. And as far as the calculator directions, there's a lot of muscle in the TI-84 using that stat button and the variables button, especially the Y equals, to come up with all of those prediction values for you. You don't have to do it by hand. That would be super time consuming if you had a very large data set. I think anything over 5 data points would start to get very ugly very quickly. So let the calculator do the heavy lifting for you. If you need to go back and rewatch certain parts of this video to practice some of those calculator keystrokes, don't be afraid to do that. And of course, ask me questions if you need to. Thanks, guys.